Good afternoon. Am I audible? Am I audible? Okay. So let us wait for 1 2 minutes. Maybe someone else will join, and then we can start today's session. So I think let us start today's session. Good afternoon. I'm Adnan Farooq Khan, and I'm pursuing PhD from IIT Delhi. And this is the seventh problem solving session for the course, Design of Power Electronic Converters, which is being taught by Professor Shabri Nath from IIT Guwahati. Like every week, this problem solving session is being carried out like from 3 on every Sunday from 3 to 5. And like every problem solving session, first we will be going through the contents that were being taught during this week, a brief overview of the contents which can then help you in solving the questions and brush up your this whatever has been taught during the week. And subsequently we'll be moving towards the question and questions, and which can then help you in uh, solving your assignments. And I can see like more there are not a number of people that have joined, and this session will be recorded, and they can like watch after that later. So coming towards the today's session, like during this 7th week, what was being taught was the EMI, electromagnetic interference. So what we mean by electromagnetic, what are its causes, uh, uh, how this EMI is generated in power electronics, because like here we are, our main focus is on the power electronics. What are the effects like it will have on the different devices, and so on and so forth. How we can limit these EMI, how we can limit our AMI, how we can design the filters in order to like limit the effect of these EMI on our devices, and so on and so forth. And ultimately, like these EMI should not affect the operation of our converters. Then subsequently we'll be seeing certain design solutions or filters that are already told to like limit and attenuate these AMI. And we'll be discussing some of the EMI filters that we use in our power electronics, how they operate, and how we design these filters. Then subsequently we'll be moving towards the question and answer session, and we'll see certain questions pertaining, and those questions should help you in solving your assignments. So yeah, coming to the introduction of the EMI. So as you can see, what do you mean by what? Firstly, like we'll look into the what is this electromagnetic interference, and how this electromagnetic interference is generated. And usually you can see this, what this electromagnetic interference is a disturbance due to electromagnetic effects. Like there are certain electromagnetic effect, like you can see inductive or capacitive electromagnetic effects, and electromagnetic effects. We'll see what are the causes of these effects. And usually the causes of these electromagnetic effects are like the switchings, like high dV by dt or high di by dt in our circuits, and which may generate a certain voltage and currents, and which can subsequent, and these are usually at very high frequencies, and which may subsequently be generated at one part of our converter, or may be generated in some other converter or some other part, and which can affect then our other parts of the converters and their operations, and which may result in the mal-operation of our converters, and so on and so forth. And that may hamper the operation of our converters. So yeah, like you can see here that the main and the main on this these electromagnetic interference is usually like how this can travel from one part to another is usually by two means. One is the conductive, and then another is the induct. One is conductive and another is the radiated EMI. So firstly, like we will see how this we'll see about this conductive electromagnetic interference, how this comes into the effect, and how this is propagated. Like I first told you, like this EMI is usually due to this can be inductive and capacitive. Usually, like you can see, there may be an inductance in our system, and we may have a current carrying coil. Like due to that, there will be a current flowing through the coil, and there will be a change in the current from one level to another level, and which can cause the introduction of an voltage and or current that which can subsequently lead to the flow of the current that will then flow from one part to another. In a similar fashion, that was about the inductor. And similarly, if we have a different potential at two different paths, and you can see between those 2 points, there will always be some dielectric. And if we have a potential difference between 2 points, there will be some capacitance, and there will be some capacitive current that will be flowing through this. And this can lead to a capacitive current which can flow from one part to another part, and this can hamper the operation of the other device or some other component. And usually, one is that there may be a proper physical connection from the source that will be the that will generate this EMI due to the high dV by dt and di by dt in our voltage and currents in the converter. And there may be a physical connection from that source to another part, and this these currents due to these dV by dt or di by dt getting generated, they may travel from one part of the converter to another part, and can affect the operation of that device, a particular device or a particular converter, and can help which can lead to the mal-operation of that converter or that part. The other thing is, like, we have a source where this EMI is getting generated. As we know, this EMI is getting generated at very high frequencies in the range of higher hundreds of kilohertz and so on and so forth. And this source can then act as an antenna, then which can radiate this from that. And but this radiation is a very ineffective one, but certainly can affect the operation of other devices. And the victim will this EMI radiated from the source will then travel to the victim, and it will depend upon upon this the placement of the source, where this is sourced from the victim. It can be a very far, or it can be very close to it, and which can then lead to the extent which it can affect that particular component or a particular part of this converter. So in this way, there are two ways of this EMI. One is this conductive, and another is this radiator, which we saw. And in one part of the converter where this EMI is getting generated, where electromagnetic interference is generated, that is called a source. And the parts that get affected due to this are usually the victims, or the receptors, or the sink. So you can see where you will see different frequency spectrum, where what are the different frequency spectrums, what are the different harmonics in these spectrums, and where this our EMI will lie. So if you can see this frequency spectrum, like if we have any grid connected system, we have a grid connected at 50 hertz or 60 hertz, and usually with that grid we won't get a very proper sinusoid. And with this fundamental voltage, there may be some harmonics associated with that, that will be ranged from this grid frequency to up to 1 kilohertz or 2 kilohertz. These harmonics are associated with this fundamental, which may affect the shape and the power quality of our grid. And And then there will be our converters, like which are switching at very high frequencies, and we'll be having different switching frequency components. And if we have a frequency component that lie between the 150 kilohertz and 30 megahertz, then these lie in the range of conducted EMI range, where we have EMI is getting generated. And if we have a physical connection between the source and the sink, and these whatever the noise or the voltage that are being generated due to the change in the voltage and levels of the converter at that particular path may get propagated from that part to another part. And if you have a physical connection between them, and then this can affect the operation of that part. And that usually this conducted EMI usually lies in the range of 150 kilohertz to 30 megahertz. Like these are the boundaries, and these are like the flexible boundaries. These are not the actual, like it can affect like below and above some frequencies below and above that as well. So now if we have the frequency components which are above 30 megahertz up to the gigahertz level, then this source can propagate this disturbances, or whatever this magnetic interference, magnetic like effect, be it inductive or the capacitive, has the property like it can propagate it through the through the medium without any physical connection, by the means of radiating it from the source to the sink. So yeah, if this frequency component is about the 30 megahertz range, then the source is able to propagate this via medium of air, or without any physical connection, and then that can affect the victim, other part, or other component or other part of the converter. So this was about like the electromagnetic interference due to the electromagnetic effects, like inductive and the capacitive, like how these are generated we will see. And there are two types, like they have a conductive and the radiative. Radiative, where in the conductive we have a physical connection through which these get propagated and affect the operation of either the part or the converter. Now, there's another term we call it electromagnetic compatibility, that is EMC, where we see if our converter and this is electromagnetic compatible or not. And what we try to do is to make there is a certain limit, or there is a certain uh, provided for every like converter, and so on and so forth, and certain standards which we have to meet, and we have to keep our EMI between below that thing. If our converter are not able to meet those standards, then those converters cannot be put into production, and cannot be put up in the market, because then these can affect other components, like if we have a certain power electronic converter at a place, and there may be some telecommunication line nearby, and if the EMI is not under the limit, then the EMI that is being produced by that converter may affect the telecommunication line, which can hamper certain operations, and which we don't want. So we have to always keep this EMI under the check, and there are the certain standards that have been provided, and we have to keep our converters under those. We have to meet our converters. Our converters should meet those standards. So usually, like in the EMI, like we'll be having a source. There will be a source, there will be a receptor. Source where this EMI is getting generated, and there will be a receptor, or a part of the converter, like which receives this EMI, and there will be a path, a coupling mean from the source and to the receptor, and this can be conductive, or this conductive or radiative. But what we want to achieve is we want to control this. We can control this EMI at three places. One is at the source. One is NSS. Someone's mic is open. Can you please like turn off your mic? So, am I audible to everyone? Am I audible? Can anyone reply, please? Hello? Can anyone reply? Can anyone reply in the chat, please? Okay. So, if there is any discrepancy in the audio, or you are not able to see the screen, kindly let me know through the chat. So if so we can like limit these EMI at three places. One is at the source. So if we want to like we want to attenuate these EMI at the source itself. Another thing is like what we want to achieve is like we want to have a source like which is not be able to produce this EMI. But if this EMI is still getting produced at the source, the other thing is like the coupling mean or the transfer path from the source to the emitter. Like we want to have a higher you can see a higher resistance or to that EMI, so that this EMI may not reach from the source to the sink or the receptor. So our coupling path should be able to produce a high amount of the attenuation to this EMI, and so that it may not affect this other part or other component. If there we are also not able to like attenuate this, and if somehow this EMI is then reaches to our receptor or receiver, our receiver should have the ability to like withstand that EMI, like the operation of that part component or that part of the converter should not like get should not get hampered or affected by that EMI. So like we have the three like path source. We want to limit our EMI in that part in itself. Then in the coupling path, we want to produce as much as the resistance or the as much as we want to hamper this EMI in that path, or if still EMI reaches at the receiver end, so our receiver should have this should be able to withstand that EMI whatever is getting generated as the paths and reach it, and it should not malfunction with that EMI. It should be able to withstand that electromagnetic interference. So this was about this now, like about this EMI. Now we want to measure this EMI. Like usually this EMI is measured in decibels, like in the logarithmic scale and in the microvolts. Like usually this whatever the voltage that's been generated is very small, like in microvolts, and it is in case of the conductor it is measured in like decibel microvolts. And usually this voltage in decibel microvolts is between 20 log, and whatever the voltage of this EMI that is being measured, which we see how it is measured by the setup that we'll see. Then we'll take the log of that voltage, and we multiply by the 20, and this is in the logarithmic scale. We called it as the decibels, this unit. And if this is the radiated EMI, then we measure it in dB microvolts per meter, because like I had already told, the receiver, how far it is from the how far it is from this source, how far it is from the receiver, also matters in case of the radiated EMF, because like the distance between the source and the sink also plays a vital role there. Because if the source is very far from the receiver, then it may not be able to affect that component to that extent. If that source is very near to that component. So in case of this radiated EMI, like it is measured in dB microvolt per meter. So in the measure, like we can measure like different things like we can measure the peak of this signal, like we can have the peak detector, and we can measure the peak of the voltage. Also, like we can measure the we have this average detector reading. Well, we can measure the average of this EMI that is getting generated. But we can see for different waveforms, we can have the same peak as well as the same average, but the frequency of these waves can be uh, different. So there should be some other measurement by which we can differentiate these two waveforms or waveforms. So the other measurement that is taken into account is this Cauchy peak. So this Cauchy peak not only takes it is similar to an RMS that we see that we calculate in our switching voltages or currents and so on and so forth. Uh, or what this Cauchy measurement takes into the account. It not only takes account into the voltage level of this EMI wave, but also takes into the effect the frequency of this wave. So if we can see here in the top wave, we have the higher frequency. You can see the Cauchy average is higher compared to the lower wave, because the frequency of this lower wave is less than that of the top wave, where it is at the higher frequency. So the Cauchy average is higher for this top wave. So these were some of the measurements that we look into this EMI. So the measurement setup that is being used to measure this EMI is called LISIN. It is the line impedance stabilization network, where usually you can see is we have an isolated setup which is shielded from the which is shielded from the outside interference. Like the setup is made in such a way so that if there is any EMI outside, it should not affect it should not affect this the device inside. So what we usually have, we have an electrically isolated table on which we put this device which is under the test, and which is connected to this license. And from the license, like we take a connection to the spectrum analyzer, and we see what kind of this in the spectrum analyzer, we see the EMI levels or EMI waveforms, and from that, like we calculate the in the decibel, like we in the measured unit in which this EMI is measured, and we see the what are the EMI levels at particular frequencies. So how this license looks like, license is nothing but usually it is like a low pass filter. What happens is, like I told, this EMI is usually at very high frequencies, and this license acts as a low pass filter, and this device under test is connected to that license. And you can see like this passes through this uh, EMI is like getting passed through this low pass lower frequencies are passed, and this high frequency EMI components are filtered through this, and from that we take this connections to the spectrum analyzers, and this on that we see whatever the this EMI that is getting filtered, and we then see that on the spectrum analyzer, and we see the different levels. So here you can see the EMI measurement plot if we for a device that is put on the test on the license. So here on the x-axis we have the frequency, and we have an amplitude in the decibel per microvolt. So we have a certain you can see like for the different frequencies how this waveform varies on the spectrum analyzer. So usually like you can see this by this red line, like like I told, there are like a number of standards for this EMI compatibility, and these devices should be able to like these are converters should be able to meet those standards. And one such standard is CISPR 22 class B standard. Here you can see at lower frequencies this is higher, the limit is somewhat higher, and at this medium frequency range limit is EMI limit is somewhat lower, and this limit goes higher at the higher frequency range. So here you can see these waveform that we have that has been analyzed is lower than this the set limit. If this limit these waveforms are above this above the set limit, then the device has not passed the test, and this device like or particular part of the device cannot be put into production. And we have to then mm, see for the different means by which we can limit this EMI in that part of the converter, or part of the converter, so that our EMI requirements are under the limit. Then only this EMC standard, like I told you, electromagnetic compatibility standards are met, and then only when these standards are met, and then only the device can be passed and can be further put into the production. So this was about EMI and certain electromagnetic compatibility standards that we had seen. That was in the general, but usually what we deal is with the power electronics here, and we want to see this EMI in the power sorry EMI in the power electronics, what are the main causes for the generation of this EMI, and how these EMI affects the operation of the converter, and so on and so forth. So usually in here on the right side is the circuit of is the buck converter circuitry, and below you can see the switching voltage and current waveform. And usually like this EMI in the particular part of the converter is getting generated due to the switched voltage and currents, uh, and some parasitic components associated with these components, because like I told you, like we had discussed in the previous sessions as well, like no component is ideal. There are some of the parasitics that are always associated with the components. So firstly we're looking about this switched, like I told you, like the main cause of the this EMI are the switched voltage and the currents, because we see like our converters operate at very high voltage and current levels, and these voltage levels change in very small during a very small time interval, in the nanoseconds interval, from one voltage level or one current level to other current level. And due to that there is a very high dV by dt and di by dt in the di by dt and dv by dt and di by dt in that part of the converter, and which results in this EMI, and which are then propagated through mm, some connections to other parts of the converter, and can hamper and can affect the operation of other, like it is some sort of a, you can say this in the crude way, like this EMI is some sort of a noise, and which gets propagated to the other parts of this other part components are part of the converter, and hamper the operation of that converter. So now we shall see about these components. Here you can see like we have different MOSFETs, diodes, inductors, and capacitance, and we know that no components is ideal, and there are always some parasitics associated with these components, like uh, here you can see, let us take an example of this inductor. Here we can see the potential at the two ends of the inductor, and two ends of the inductor is different, and there will always be some dielectric between these two ends, and it will form a capacitance, a parasitic capacitance between these two ends, and there will be a capacitive current that will flow through, and parallel parasitic capacitance will get formed across this inductor, and these may then resonate with this other part of this inductance, some parasitic inductance, and also there will be some capacitive current flowing through, parasitic capacitive current flowing through that capacitor, which and if the dV by dt and di by dt at that particular node is very high, and uh, even if the value of this inductor and capacitor is very low, still if we have a very high dV by dt and di by dt, whatever the current or the voltage that is being getting generated will be of some appreciable amount, which can then affect the operation of a particular component. And not only that, there are other, like this converter will have some chassis, or will be enclosed in some enclosure, and that will be grounded, and between these components and to that chassis there will be some capacitance to that as well. And not only that, if we have this MOSFET, it will also have some parasitic capacitance and the inductance. Also this capacitance here, it will have some parasitic resistance and inductance, and besides that the leads or the leads of the converter will have some inductance, parasitic inductance as well as the parasitic resistance. And if we have the traces, there will be some parasitic inductance as well. So this parasitics cannot be avoided, but we shall always try to look to minimize these parasitics, and this you'll see in the subsequently, like by properly designing the converter, like not placing the components too far from another, have the very compact design, and take into the account certain things that we'll see in the subsequent slides, and next week lecture as well. Like how we can avoid these things, and we can see in the subsequent slides as well how we can limit this EMI. So this as I told you, like these leads and etc will have some parasitic inductance, and if this dV by dt or di by dt is very high, then we can have appreciable amount of this EMI. Like these leads can then lead to, if the switching frequency is very high, like then firstly we can have a conducted EMI. Then if the switching frequency is in the range of megahertz or so, then we can have this. And if this di by dt is very high, like then this can subsequently lead into the radiated EMI as well. So this was about like in the power electronic converters, like how this EMI is getting generated. It is usually mainly due to this dV by dt and di by dt of this switched voltage and current, which causes like a very high in the SMP and switch mode power converters. These switching voltage and currents are like switching intervals are very high, where this voltage change from one level to another, or current change from one level to another in a very small amount of in time, like in the nanosecond, and which can lead to very high dV by dt or di by dt, which is the cause of these EMI. So firstly, we'll look into the uh, common mode and differential mode noise, what is being generated. Let us say we have a power electronic converter, and what we'll be first having, will be having the line, and we'll be having a neutral, like I told you, and there will be another is the ground. Our power electronic converter will be enclosed in an enclosure, and this enclosure is usually grounded, so that there is not any any shock, or if when someone holds this converter or tries to work with it, and a person may not get a shock, or so on and so forth. Usually what happens is we usually have this line and neutral voltages may be at some potential with respect to these ground, let us say V1 or V2, and V1 and V2. Usually what we have is then we can have we are usually have this two voltages, like common mode voltage, which is given by V1 plus V2 divided by 2, and there is another is the differential mode, that is V1 minus V2, which we usually see, whatever we usually have seen up till now, a voltage we see is a difference between the two potentials. And in terms of the currents, usually what we have seen, and is this through the line, the current will go into the converter, and through the neutral, the current will come out, that is the usually the current. But there can be, due to this EMI, there can be some currents in the line and neutral, which will be in the same direction. uh, so that are that is are known as the common mode currents. In this common mode, in the currents, the common mode current is given by the I1 plus I2, and differential mode is given by I1 minus I2 divided by 2. If you see, if the I1 is the current going into the converter, and this I2 is equal to minus I1, that we usually see this, then this differential mode is equal to 0, and we can see common mode is equal to 0, because I1 will be equal to the I2, and this the direction is opposite, and this common mode may not be there. But if there is some current that is flowing in the same direction into the line and the neutral, then there is then this common mode current flowing into the converter, and it's given by I1 plus I2, and the differential mode is then given by I1 minus I2 divided by 2. And you can see here, we can take an example of the buck converter, as has been shown here. Here we can see the current paths in these different parts of the buck converter, and we shall look into here. If we see the top part, this is usually what we see. We have a buck converter, and the current will flow from the source through this, the switch, and then inductor and the capacitor or the load, and then go back into the source where the neutral line. And this is usually the differential mode current that we talk about. But as we had seen, what we had seen, there is always, with respect to line or the neutral, there will be another with this converter is usually enclosed in the enclosure, which is usually grounded. And because of that, this line and neutral will be at some potential with respect to that ground, and there will be certain capacitance that will be getting formed. You can see here that will be represented here. And what we see, if you can see this, the node here, after this, the switch, diode, and this inductor, this node is usually a switching node. What we call is the switching node is where this voltage or the currents are in the switching, are switching, because whenever the switch is on, the voltage will vary from 0 to VDC, and in a similar fashion, the current is a switching current at this portion. And because of this switching, there will be a very high dV by dt and di by dt at this node. And because of this high dV by dt and di by dt, there is also some parasitic capacitance, and the current will flow. And you can see the path of this common mode current will be through the switched node, and it will, because this dV by dt and di by dt, this is getting generated at a high frequency, and this parasitics will provide a very low impedance path, and it can flow, you can see, flows through this parasitics here. And comes back to this, like the devices and into the source. Like this is the path of this common mode current that is getting that flows through the converter. And usually, like what we want to do, we want to minimize this common mode as much as possible, because this is not what we usually want. We want that the operation should like this, the top one in the differential mode, where whatever is going in it comes out through the neutral, and there should be minimal this common mode currents in it, and we want to always minimize this thing, because it can affect the operation of the devices and other components as well. So here you got the idea of this, the common mode and differential mode noise that is getting generated in the converters, and what are the different paths through which it flows. So moving forward, like we will see the different frequency ranges at which like these components are, like firstly, like we'll be having the switching frequency, which is like usually into the kilohertz, hundreds of kilohertz range. And after that, like there will be some component resonance. Like I told you, there are some parasitic inductance and capacitance which may then resonate among us themselves, and usually these are around like megahertz level, like the resonance, because the value of these parasitics are very small. And if you can see, this resonant frequency will be given by 1 by root LC. Omega resonant will be equal to 1 by root LC. And if these smaller the value of these components, higher is the frequency, resonating frequency. And then there are like PCB layout resonance, because of the PCB layout, if we have the components and there are physical connections between the done through the wires and so on and so forth, that may have higher parasitic. But usually with the PCB designs, we have the very compact designs, and this value of these parasitics are smaller compared to the converters made with the physical wires and so on and so forth. So if we have the smaller value of this parasitic inductance in the capacitance, so the resonance in the PCB layout will be higher compared to the component resonance. That's why they speak at very high resonance, as high resonance. So these usually what we see is usually the common mode noise problem, which is due to the parasitic capacitance. And these are at very high frequencies, because like high frequencies. And this usually this differential mode noise problem, like which are usually due to this parasitic inductance, are at lower frequencies, not that lower, at around megahertz and hundreds of kilohertz level. And this common mode noise problem dominates at very high frequencies in terms of tens megahertz or tens of megahertz. So now we shall see about like what are the different solutions that we can opt for in order to eliminate or limit these EMI problems. First is like we may use like a particular EMI filters, like which we'll subsequently see in the which we'll see in the subsequent slides. What are the different filters, how we use them to limit or eliminate these EMI. And the second thing is we want to have the enclosure, like I told you, like you can have a we want to enclose our converter, so that like you might have read about this Faraday cage and so on and so forth. And we want to have the metal like enclosure. So if the other converter has generated some EMI is being generated as some other part, so it may get propagated to a particular part. But if we have a enclosure, and this enclosure does not allow the EMI, so we shall be able to like isolate a particular part or the component from that EMI, and thereby like limiting that EMI. Sorry, 1 minute, please. And thereby screen not visible. Is it visible now? Is it visible now? Can any other person also confirm that screen is not visible? Because I see. Just a minute. Is it visible now? Sorry. Yes. Just a minute. Is the screen visible now? Is the screen visible now? Yeah. So kindly let me know, like, if sometime like the screen is not visible or not. So now we can see like different. This happened as of now. So you are able to see the previous slides, or do I have to go through them again? This happened right now, or you were able to follow previous slides? Okay. So coming to this design solutions, like I talked about this EMI filters and then this enclosure. The other thing is like the PCB layout. PCB layout is like a very important thing, because like like we want, you can see like at where we talked about this switching node, and this is at very high frequencies, and usually like high frequency currents will flow in this loop, and we want to minimize this loop as much as possible, and so on and so forth. Like we want to minimize this switching loops, so that these loops are as small as possible, so that our parasitics are reduced, and in which in turn will reduce the EMIs. So PCB layout like plays a very vital role in this, like which we'll see in the subsequent week about the PCB design, how it is done and so forth. But you can see like this, we have to do the PCB design is to be done in the proper way. The other solution is like we want to have the shielded cables, like you can see here in the top, like we have a number of braided wires, and these braided wires are like then enclosed in this foil shield. So like the main purpose of this shielding is like, if we have like the two wires next to each one another, and there is some magnetic field that is being generated from one wire, and that should not affect the uh, that should not affect this line as well, like that magnetic field, and we want to shield these wires from that, and that is the main purpose of the shielding. And the shielding is done in the wires, and the shield also is done in the enclosures as well. Also the other thing is to have the twisted wires, like usually if we have like if you can see the this bottom picture, like we have two lines, one line and the neutral, and if they are not twisted, like if they are running parallel to one another, you can see the current is flowing in the one direction and is coming out of the one direction. If we apply the right hand rule, and you can see the magnetic field of the both lines is in the same direction, and which aid each other, and subsequently which can like generate the higher EMI because of that. Now with respect to that, if we have the twisted wire, here you can see a number of loops are made, like one is in the clockwise direction, one is in the anti-clockwise direction. You can see that the magnetic field that is being generated in the different adjacent loops is in the opposite direction, which then tend to cancel one another. And then if there is a very high switching and this magnetic there is like tend to cancel each other, then ideally we can say there is no magnetic field, and which can drastically like reduce this EMI problem. The other thing is like proper grounding, like we saw there is a parasitic capacitance between these components and line and the ground, and if the proper grounding is not, with the proper grounding we want to minimize these parasitic capacitance as much as possible, and as such this proper grounding is very vital and very important in and should be properly designed. The other solution is like the gate resistance. Like usually you can see we saw this usually this EMI is getting generated because of the switcher voltage and the currents, and usually like this device turn on and turn off, turn on and turn off is very small and happens in the very small duration of time in terms of the nanoseconds, and in that small time our voltage levels change from one level to other level. So one way is to like we want to increase our turn on time, and which may then like reduce our dv by dt and di by dts. And one way to do that is we want to we want to have the higher gate resistance, and because of that this our CGS capacitance will take more time to get charged, and because of that our turn on time will increase, and due to that due to the higher turn on time, like our dv by dt, now our voltage and current will take a higher amount of time to turn on and turn off, which can subsequently like lower the dv by dt and di by dt, and thereby like reducing the EMI. But the downside of this thing is because of this increased turn on total turn on time, we can have the more loss, we can have more switching losses that we had seen is dependent on the turn on and turn off time, these switching losses. And now what we do is we want to have find the optimal point where this EMI is also reduced and we can have those smaller losses as well. The other thing is like the snubbers that we had seen in the previous slides are also used to like limit the dv by dt and di by dt, which can also like help in reducing this EMI problem. The other thing that we'll see in the question is the soft switching. So what happens in the soft switching is usually like we change the voltage level or current level from one level to another, and usually it is from like 0 to very high level. And but in the soft switching what happens is like we first like the voltage or current level is decreased to a particular level, we want to decrease this voltage and current, and then ideally we want it to be zero, like one voltage to be zero, and then we want to switch our device at that on time only, because then the dv by dt will be very less. And in that way, like if we switch at now at lower voltage and current levels, then this dv by dt and di by dt will be lower compared to the ideal hard switched case where this voltage and current switch from one level to higher levels, and which we can have the higher dv by dt and di by dt in that case. This we shall see in detail in one of our questions, and in this way, like this soft switching also aids in reducing the EMI. The other thing is random PWM. As you can see here, usually we see in the PWM is usually in the repetitive. uh, fashion. But if it is in the repetitive fashion, then the noise is getting generated at a particular point, and it has a particular. See, if you can see here, this spectrum shown in the black, you can see we have this peaks at a particular interval because of this. If we have a normal PWM, but if we have the distributed or the random PWM where no such pulses are getting generated repetitively, then this noise may get distributed, and if it may not be concentrated at a particular frequency level, and as such there may not be this sort of a peak in this random. You do not see this high peaks in this random PWM, but this what happens is this noise is getting distributed because of this over the whole spectrum, and in this fashion, like we can, this is also one way where we can eliminate this EMI. So this was about different solutions that can be implemented. Now we shall see one by one see this solution. One is this EMI filters. Uh, One such filter is like the common mode choke. So what is this common mode choke? This common mode choke is nothing but you can see, if we have a toroidal core, and we have the two wires, and we want to we wound these two. We have this like two wires line, let us say line and a neutral, like we'll wound it on this core. Now what we had seen there will be a common mode current or voltage, or and one will be a differential mode. So if we have the differential mode, what the direction of the current through these two wires will be in the opposite direction, and because of that, if we wound here, if you can see on the right hand side, because of these two wires having the current in the different directions, what happens is the magnetic field that is being getting generated, the flux that is being getting generated is in the opposite direction, and they tend to cancel one another. So this differential mode does not see, ideally does not see any inductance, and as such no impedance for higher frequencies, and as such it won't filter out these this differential mode. But what happens in the common mode noise, this, as the current in the two wires is in the same direction, and the magnetic field that is being getting generated is in the same direction and aids one another. So these two will see an will see an inductance, and at higher frequencies a very high impedance, uh, a very high impedance to these common mode noises, and thereby because of this toroidal core will have an inductance, and at higher frequencies which will provide a very high impedance to these common mode noise, and thereby limiting these common mode noises in that particular part. This was about this the common mode choke, how it's implemented, how it limits this EMI. The other is this the common mode circuit that can be implemented is the EMI filter example. Let us say we have a power electronic converter. Usually we see the power electronic converter between the source and the load, but here the power electronic converter is an EMI source, because this is the switched network, and EMI is getting generated here only. So here it is called as the EMI source, and usually here it is licensed is take as a load, but usually it may be connected to other parts of the converter where this EMI may get propagated, and in between that is the differential mode or common mode EMI filter, which is usually you can see we have a common mode choke for this common mode choke for this common mode uh, this what I say is common mode noise, and then there will have some inductances for the, that will be the simple inductances for this differential mode noises, and we have here we can see we have the two capacitances. One capacitance is connected between this line and to the neutral, and this capacitance is known as the X capacitance. And you can see the other capacitance is between the line to the ground. Usually, like we know, like this ground and the line are different, and this ground is usually connected to the chassis, and the capacitance that is between this line or neutral to the ground are known as the Y capacitances. And also will be have some damping this uh, uh, in this, because like we know this there will be, because of this filtering capacitance, filtering circuit will have some resonance, and if there is not proper damping, then these resonance may persist on for some time, and can make our operation unstable, or can hamper the operation of the converter. So we need some damping to damp out these damp out the resonance. So how this circuit looks like in the differential mode and the common mode is towards the left. If we have the differential mode, then the current goes through this one end and comes out through the neutral. And we know this like common mode, we have seen earlier in the previous slide, this common mode will not provide any filtering or impedance to the differential mode, and only the leakage part of that common mode will affect will be there with this differential mode. And you can see whatever the current that is coming to the line is coming out to the neutral. So we can see this differential mode inductance can be lumped together as together, therefore like plus twice LDM. And this differential mode of does not flow through the ground, so you can say this CY and these two CY capacitors are connected in series, so this will be equal to CY by 2, and this will be in parallel with this Cin, so CX plus CY by 2, and there will be some damping associated with it there. This is the equivalent circuit of the filter that we'll see in case of the differential mode noise, and which is this circuitry is then used this circuitry is then used to look into this circuitry is then looked into and solve for solve this network is then solved for putting this differential mode, analyzed and solved for differential mode noise. And in a similar fashion, if we have a common mode noise, then this is being filtered by this common mode inductance, and since this common mode current will be flowing in the same direction through this L and N, we can say this LDM will be in parallel. So as such, there will be LDM by 2, and this common mode will flow through this Y capacitance, and we can see this Y capacitance are in the parallel, as such this twice Y. This is the effective filtering circuit for this common mode EMI filter. So this was about the different filters that can be used in the common mode, and this was a generalized filter if we use in the for filtering example, and what is the effective circuit in the differential mode noise for the differential mode and common mode noise. So usually what we see is the like I told you, we have a power electronic converter and there is a source, and in between them there is a EMI filter. And usually what we want this power electric converter will be the source of this EMI, and there will be some impedance of this power electronic converter, and we'll be having a load or some other part or the grid or whatever, they will have their own impedance. So there will be two impedance from the source side and the load sides, and in between them there will be a filter. So what we want this filter to have an impedance in such a way so that this EMI is getting eliminated through this filter, and it will not affect the other parts. And what is done is this impedance mismatch is done by this EMI filter. So you can see here, like if we have a source that is having a high impedance, and our load is also having the high impedance, so how we want our EMI filter to look like? So we have a so the source and the loads are providing the high impedance to the high impedance EMI. So what we want, we usually will want an EMI filter that will provide the low impedance, because like if the source and load will provide a high are having the high impedance, so what we want it to have is the low impedance, through which we should be able to like filter out this EMI. In a similar fashion, if we like have the low impedance at the source and the low impedance at the load, so what we want to have this filter, so this filter should have the high impedance, so that this can eliminate, or this can limit this from this EMI from this source to the load, so that this EMI is not getting propagated from the source to the load, because this filter will then provide a high impedance to this EMI and filter out that EMI. So this was about like the filter, which were different filters depending upon this impedance at the source and the load. We can have the different filters. We can have the different filters of different impedances to eliminate, or to eliminate this EMIs, eliminate this EMI problem. In the similar fashion, we can have the higher filter with the higher attenuations, like we can have the third order filter with the 60 dB attenuation, which can provide the higher attenuation to, if you can see the body of this of a third order, like it will have a slope of a 60 dB per decade. So for a particular frequency, this is able to provide 60 dB will provide 1,000 times more attenuation to this 20 dB filter. This is similar filter. We can have a pi sort of a filter, pi network or a T network, which is usually a third order filter, and have attenuation of 60 dB, thereby providing a higher attenuation to this EMI. So the other thing is the final thing that was being taught is EMI filter insertion loss. This is not an insertion loss. This gives us the measure of the attenuation that is being provided by the EMI filter. So it is being given insertion loss is given 20. So if we have the how it is done is, if we have the two networks, we have the source and the load. What we see is, if there is a filter, between the two networks, we can see these two as the two port network, and if we have the filter between them, and without the filter, what is the EMI that is getting generated at the load side in the two cases. And what we do is, insertion loss will give the 20 log V2 dash, that is the EMI that is getting generated, which we so know without a filter, and V2 is the with filter, and it is given by the 20 log of the ratio of that, and we know it's in the decibels. And for the insertion loss is also given, if we can see, we have this two port network, and we know like we can have the different impedance solved for the two port networks, and insertion loss is given with this equations. So this was about the summary that is being done. Now we shall move towards the problem solving session. Let us take like a 5-minute break, and we shall join at 4:20 and move towards the problem solving session. We shall take the 5 minutes break, and we shall 2-3 minutes break, and we shall join for this problem solving session. Is the screen visible? So we can move to the first question. The first question is the frequency range of the conducted EMI is. Like I think you should be able to answer this question. Like we had discussed in here. A is 50 kilohertz to 2 kilohertz, 150 kilohertz to 30 megahertz, 30 megahertz to 1 gigahertz, and 5 hertz to 50 hertz. So if you can see, the answer to this question is 150 kilohertz is and 30 megahertz. What we had seen is like we saw is usually this EMI is conducted EMI, and usually it is getting by generated by two effects, capacitive or inductive effect, and it can be like inductive or the capacitive. And we have seen in the range of like 50 hertz and to a kilohertz there will be harmonics, and which can affect the power quality and so on and so forth. Then in the range of the 150 kilohertz to 30 megahertz, we have seen the predominant are like this conductive, and then if we move towards the higher frequencies of 30 megahertz to 1 gigahertz, then the radiated EMI is usually in that range. So the answer to this question is like B, 150 kilohertz to 30 megahertz. Question number 2. Radiated EMI is measured using Lyson, antenna, 2 wattmeter method, and stroboscope. So I think like this we didn't cover in the slides, but because this was here, so we can see, we saw here in the conducted EMI, we had like a proper setup, like in the isolated setup or room or so on and so forth, where we had an isolated table. On that is the device and the setup, and that is being connected to the license, and through that, like the EMI part is isolated, and which is then transmitted to the transmitter to the spectrum analyzer, where we see that EMI. But in case of the EMI, radiated EMI, what we have the still this is an isolated room or isolated setup, and we have the device under test on this on the table, and this device under test is not physically connected to any device, but there is an antenna that is being provided, that is being held nearby. And we also saw like it also depends upon the placement of this antenna and how far this receiver, like that antenna, is from this the device. And as such, like we saw the unit of this radiated measuring unit of this radiated EMI is like decibel microvolts per meter. And this EMI generated from this source is transmitted to this antenna, which acts as a receiver. And from that, like we have this spectrum analyzer is getting attached to that, and we get the measurement of this EMI. So the answer to this question is an antenna in case of the radiated EMI. So question number 3, which of the following is the main source of common mode noise? One is the parasitic capacitance, wire resistance, high power levels, and long cables. So all of these are some reasons for the generation of like the source of this common mode noise, like but we have seen long cables will have some this parasitic inductance, and which may generate some EMI. Power cables, high power cables, will also have resistance. But the main source of the common mode noise is the parasitic capacitance, like we saw here in case of the buck converter. Like we had the switching node, we are switching at a very high frequencies, and the voltage levels and power levels are changed in a very small amount of time, and there is some parasitic capacitance that are getting generated between between these line and the ground, and due to these parasitic capacitance provide this path for these common mode currents to flow, and because of this capacitor, and as such, like these parasitic capacitance are like the main source of this common mode noise, because at this node there is a very high dV by dt and di by dt, and common mode noise like gets flows through this generated flows through this parasitic capacitance, as such being the main source of this parasitic capacitance. The question number 4 is increasing the MOSFET gate resistance in the power electronic converter can lead to reduced EMI, reduced switching loss, increased EMI, reduced switching loss, increased EMI, increased switching loss, reduced EMI, increased switching loss. Can anyone answer this question? I think you should be able to answer this question. Like we discussed this. Can anyone type? So what we saw here is as we like I told you, like the CMI is depends upon the switching voltage and currents, and with high dV by dt and di by dt, we want to like decrease this dV by dt and di by dt, and one such way is with insertion of this gate resistance. And if we increase this gate resistance, then it will take more amount of time to charge this with GCS capacitance, and if it takes more time to charge this GCS capacitance, and the turn on time of this is increased, as you can see by this waveform, and as we had discussed in this previous sessions. And because of this, if the turn on time is increased, and now the current will change from one level to another level over a higher amount of time, and thereby like decreasing the di by dt. In a similar fashion for this voltage, now the voltage decreases from one level to the zero in more amount of time, thereby like decreasing the dV by dt as well. But because of this high gate resistance, what happens is this this turn on time and turn off time increases, and with the increase in turn on and turn off time, the switching losses increase, and that is the downside of this. If we want to like reduce the EMI, the switching losses increase, so the option D is the correct option. Now the question number 5 is select the correct EMI filter combination depending upon the source and the load impedance. So we have like the source high impedance, load is low impedance. There is a like CL filter is used, and if the source voltage if the source has low impedance and load has high impedance, LC filter is used. If the source has high impedance and load also has high impedance, the pi filter is used. So if the source has low impedance and load also has the low impedance, T filter is used. So you have to answer which of these is correct. There can be multiple correct options. Like, can anybody answer like we had seen? So one of you have answered, and this is the correct answer to this question. So we'll see. So we had previously seen, and we want to have our EMI filters as per the impedance mismatches. So if we have a high impedance at the source or the load, we'll have the filter with the lower impedance, and vice versa. So if you can see the first, if the source has the high impedance, we want next to this source the CL filter, because C will provide the low impedance path, and for this load, this L will provide for the low impedance, this L will provide the high impedance path. So for part B, if the source is low impedance, for the low impedance we'll provide the high impedance, and for the high impedance we'll like connect like the L on the source side, and if we have the load side has the high impedance, so we will like have the lower impedance at the load side, so we'll connect a C towards this as such the LC filter. So now if the source has high impedance and also this load has high impedance, so what we'll have on the both sides we'll have a low impedance towards the source as well as the high. As such we'll implement like a pipe filter while we have the capacitor and this towards the load and the inductance at the middle. So now if this load and the and low source as well as the load have the low impedances, then we shall be having the filter which will have the high impedance towards the load as well as the this side. As such we will be implementing this pi network which has the inductances towards the load and the source and the capacitance in between. So we'll have the pi network. So all of these options are correct. So question number 6. Can you please answer this question? The unit of the insertion loss is. I think you should be able to answer this question. So the insertion loss unit is. Anybody? Yeah, the option is correct. We have seen we measure it in the loss in the dBs, and as such the option is. We have seen the insertion loss is the ratio of like if we have the two networks, one with the EMI filter and without the filter, and whatever the EMI voltage that we get at the load side in the two cases, and if we take the ratio of that and have the 20 log of that, we get in the insertion loss in the dBs. As such 6 is the correct option. Now the last question is, dash switching is preferable than hard switching from perspective of the reduced EMI. Can anybody answer? I think you should be able to answer this as well. So we had seen previously in the previous slide as well that the softs, if we go for the soft switching, this EMI it will have the EMI can reduce, because like we are in a way like limiting the dV by dt and di by dt. How so? And we'll see. Let us say like we have the two networking, like we have the hard switched and soft switching. Like if first we'll see the hard switched. Whenever the device is turned on, like one voltage level changes from one level to another, and the current rises from 0 to the rated current level. And in this, like the turn on time takes at higher voltage levels here and higher current levels, and as such like the dV by dt and di by, and this happens in a very small amount of the time, and the voltage levels are very high, and as such the dV by dt and di by dt will be very high, which can result in the higher EMI. But if we have the soft switching, what happens with the soft switching, we shape our currents and voltages in such a way, like if you take an example here, the current is shaped in the shape of a sinusoid through resonance, that the current first increases and then decreases, and when the current decreases then we turn on, and as such we can have the lower di by dt here. In a similar fashion, like we can shape the voltages through the resonance. So if the voltage first rises and then decreases, and if and then when the voltage is very less, and then at that moment we can turn on, we can like turn off the device, and therefore like we can have the lower dV by dt at that moment as well. So in this way, like from the perspective of the soft switching, we can like reduce like the voltage levels, and which can at the time of the turn on or turn off time, and which can in turn like help in reducing the EMI. And as such, like the soft switching is the answer to this question. So like this was it for the today, and this concludes our this part where we had in detail like discussed the EMI portion of the converter. If you are having any questions, like you are free to ask. and I am here for like 2-3 minutes, and if you don't have any questions, you can leave and we can close the meeting for today. So anybody has the questions, and he or she can ask. If not, then we can mm, close today's session. Thank you everybody for joining. Thank you everyone. I'm still here for some time. If anybody has the questions, then you can ask.